Hi, this is lesson 2 out of chapter 17 on redox and electrochemistry. Just to orient you guys before we get started, lesson 1 was on redox essentials. I didn't make any of my own videos for that or provide you with PowerPoint slides. Rather, we spent the virtual classroom day on Wednesday practicing the skills that you picked up from either the reading or the videos. So this is the first of my lectures, and it is on Voltaic cells. This goes along with section 2 out of chapter 17 in the textbook. And then next week, our last lesson for the semester is on the standard potentials and applications of redox chemistry. So yeah, today we're focusing on voltaic cells, which are really just simple chemical batteries. And in these chemical batteries, spontaneous redox reactions are producing electrical energy, voltage and current. So basically what we have in a voltaic cell is that we have the half reactions that we talked about during redox essentials separated so that electrons can be moved, can be pushed through wires. And that essentially is electricity. Moving electrons is electricity. So let's say we have two beakers. In these beakers, I've got solutions of a metal along with a solid phase of that metal. And we refer to the solid phase as an electrode. Let's use some terminology. Depending on which metals and which metal solutions are in the beaker, one of these beakers will be the anode. And the anode is the place where oxidation is happening. The other beaker would be the cathode, and this is where reduction would be happening. So just for the sake of argument, if I have oxidation happening on the left and reduction happening on the right, which way would electrons be moving if we were to connect these two cells? Well, since oxidation is the loss of electrons and reduction is the gain of electrons, you might have guessed that the oxidation side of the cell would generate electrons, which would then move to the right side, the reduction side in this particular drawing. So yeah, that is what we would expect. If we connect these electrodes with a wire, we make that chemical reaction happen and we make that flow of electrons happen. So let's get a little bit more specific. Let's think about a redox reaction involving zinc and copper. If we take a piece of zinc metal and we stick it in a solution of copper ions, a reaction occurs very quickly. The zinc is oxidized, right? Because we're going from zinc 0 to zinc 2 plus. So that's our oxidation. And then our copper is being reduced, going from 2 plus to 0. So that's our reduction. So if these are happening in the same test tube or the same beaker, the reaction happens very quickly, and there's not really a way to harness those electrons that are moving from the zinc, being lost by the zinc and being gained by the copper 2 plus ions. Can't really harness those electrons. So if we want to be able to generate electricity out of this reaction and harness that, we need to separate those half reactions and employ indirect electron transfer. So this is getting a little closer to what that would look like. With indirect electron transfer, we would have the oxidation happening in one beaker, so the zinc going to zinc 2 plus, and we would have the reduction, the copper 2 plus going to copper metal, happening in the other beaker. And so just like on the first little simple diagram, if oxidation is happening on the left and reduction is happening on the right, we would get electrons flowing from left to right here. But there's a problem with my drawing. As I've drawn this electrochemical reaction won't happen. And the reason has to do with charge balance. I've brought this up a few times in lab and in the context of redox chemistry. Reactions systems have to be charge balanced. So what's going on here? On the left, a whole bunch of zinc 2 plus ions are being generated. That would accumulate positive charge in the beaker on the left without anything present to counterbalance that positive charge. If reduction is happening on the right and the copper ions are being reduced and essentially plating out on the metal electrode, then we would have a dearth of positive charge in the beaker on the right, and whatever counterbalancing anions are there would no longer be counterbalanced by the copper ions. So we need something called a salt bridge. That salt bridge can take a lot of different forms. Often it might be a glass tube, such as this one here, that's filled with maybe a gel material. It might contain lots of just positive and negatively charged ions. Essentially spectator ions, could just be sodium chloride or something like that. So if we have that salt bridge, ions can flow from the salt bridge to counterbalance accumulations of charge. So, right, in this example here, if we have a whole bunch of cations and anions in the salt bridge, and we've got accumulating zinc cations on the left, they need to be balanced out by anions. So those negatively charged particles, whether they're chlorides or nitrates or whatever they are, kind of your typical spectator ions, they would diffuse out of the salt bridge and into that beaker. Same thing on the right. If our copper 2 plus ions are plating out as copper metal, leading to a lack of positive charges in solution, then the cations from the salt bridge would diffuse into the beaker on the right. So we would get migration of those ions out of the salt bridge. That salt bridge can really look, it doesn't have to be a glass tube. Sometimes when I demonstrate this in class, I literally just take a paper towel soaked in salt water and drape it over 2 beakers, and that works just as well as a salt bridge too. Another important thing that you'll see in some of the homework problems is kind of a shorthand notation for this whole setup. First thing to note is that the salt bridge is represented by these 2 vertical lines. And what's to the left is what's going on in the anode. And remember again, that means oxidation. So we have zinc going to zinc 2 plus as the oxidation reaction in this half cell. And then in the cathode, we have reduction happening. So copper 2 plus is going to copper metal on the right side in the cathode of this electrochemical cell. So let's look at just a couple other examples of what this can look like. In this picture here, we don't have a typical salt bridge. We don't have that tube or that connecting paper towel or whatever it is you're using. In this case, we just have a porous wall that might also be infused with, it might be a material that's infused with mobile ions, or you might just have electrolyte in solution. So you can sometimes achieve the same thing with a porous wall separating your 2 half reactions. Let's take a look at another spontaneous redox reaction in an electrochemical cell with our 2 half reactions separated. So in the anode, this time we have the same reaction we had before, oxidizing zinc. You can tell that there's oxidation happening because we can see the electrons in this figure moving from the anode to the cathode as they're supposed to do. And so that tells us that whatever's going on over here on the right is reduction. We know this is the cathode side of the cell, so there's reduction happening here. Now this looks a little bit different. There's 2 ions in solution, cobalt 2 plus and cobalt 3 plus, and then this electrode is made of platinum. What's going on here is the platinum is not involved in the reaction. Platinum is a metal that's very inert. It doesn't tend to interact with many other redox species. So the spontaneous reaction that's happening is the zinc is undergoing oxidation and the cobalt is undergoing reduction. So how we write that in the shorthand notation looks a little bit different, but there's some similarities. We still have that salt bridge. We still show the oxidation first, the anode side of the reaction first. and so left to right, zinc going to zinc 2 plus. And then we still show the reduction happening at the cathode to the right of the salt bridge. And again, left to right, we go from cobalt 3 plus to cobalt 2 plus. The difference here, though, is that the vertical line represents kind of the interface between solution phase chemistry and the solid electrode. And so we write both of those species separated with a comma to the left of this vertical line. And then the electrode, which is made of platinum here, is written to the right. So just to recap, a few terminology things. The anode, it is our negative electrode, and it's the material that has the higher potential to be oxidized because it's where oxidation happens. So electrons would then be flowing away from that anode toward the cathode. The charges here kind of make sense as well. If our electrons are flowing away from the anode, they're being attracted to that positive electrode, the cathode. This is a material that has a lower potential to be oxidized, and therefore reduction is happening at that cathode. And yeah, electrons are flowing towards it. And the electrons, as we saw examples of, can be metals involved in the reaction, like the zinc or the copper potentially, or it can kind of just be a conduit for electrons when it's made of an inert metal like platinum. So I think that is all I have for you guys today. We will check back in next week.